All right, this is the video recording for the topic 6.4 practice problems on heat capacity in calorimetry. Okay, so there's a lot of information in this, and of course we're going to go more in depth as we go into our other units, okay? But the main thing I want you to know here is this equation, okay? That's the first equation in the thermodynamics section on your AP equation sheet, okay? So that's going to be the most important or most useful equation throughout this unit, okay? Now, we've talked about this concept of heat, okay? And heat being the transfer of energy. Again, we talked about it in the last unit from hot to cold things, all right? And there are really three factors to contribute, or that contribute to that transfer of heat, okay? It's the mass of the object, okay? This thing called the specific heat capacity, and the change in temperature. Okay, we've said a lot that heat and temperature are very similar, but there is differences, okay? And so we're going to really look at what those differences are, okay? And the final thing we said is this thing called the specific heat capacity, all right? And what that is here is, if we look at the definition, it's the amount of energy needed to raise the temperature of 1 gram of a substance by 1 degree, okay? And Celsius, Kelvin, Fahrenheit doesn't really matter, okay? It's raising something by 1 degree, okay? And if you look at the units here, joules per gram Celsius, okay? So it's going to be some number of joules, which joules is the unit for energy, per 1 gram, 1 Celsius, okay? So the specific heat capacity is going to be used in one of two ways whenever you're dealing with AP problems. In way number one, you will be given the specific heat capacity and asked to use it in a calculation. Most likely, Q equals MC delta T, okay? Or the other is that you're given all the other information and you're asked to solve for that specific heat capacity. Again, using Q equals MC delta T, okay? So, again, that's why that's the main or most important equation right there, all right? Now, we talked about heat. It's energy flow from one thing to another, okay? And we've talked about it in different forms. We've talked about it from the hot thing to the cold thing, from the system to the surroundings to system, etc., okay? And again, the unit for heat is in joules, all right? And if we look here at this equation, this is saying that heat is equal to mass times the specific heat capacity times the change in temperature, okay? So temperature and heat are on opposite sides of an equation, okay? But they are both in the numerator, which means that they are directly proportional. So if temperature goes up, or the change in temperature goes up, so does the heat, okay? So again, that's why we've talked a lot in the beginning about that these are very similar. You can kind of make the same thing, but this is the unit where we figure out the distinction between heat and temperature, okay? Now, the way that we typically do this here is through this method called calorimetry, okay? And calorimetry is just the word for the amount of heat transferred during a reaction, or how we do that, okay? There's different types of calorimetries, okay? There's nicer versions that are more expensive, or there's some that's just really simple, like this one, okay? This is 2 styrofoam cups inside of each other with a styrofoam cover, okay? So this is oftentimes called a coffee cup calorimetry. Okay, why? Because again, coffee cup, like a styrofoam coffee cup. All right, but regardless of if we've got this kind of setup, or as you'll see later on, a really nice setup, it's still the process of just measuring, okay, the amount of heat transferred during a reaction. Okay. And in this idea of calorimetry, we utilize this first law of thermodynamics, which basically says heat can't be gained or lost. It can only be transferred. All right. And again, in chemistry, we are going to assume that we are in a perfect system where we lose nothing. Okay. So if we lose nothing, that means if we have this metal here, okay, and we can measure the temperature of the water, okay, the amount of heat that the metal gains or loses will go directly to the water, okay? And what you should notice there is that one of them will be positive and one of them will be negative, depending on, obviously, if we are gaining or losing heat, okay? Gaining or losing heat, all right? So we can set these two equal to each other. And since we know that the formula for Q in both of these scenarios is MC delta T, what we can do here is set them equal to each other. Okay, so M of the metal, which is the mass of the metal, the specific heat capacity of the metal, and the change of the temperature of metal, is equal to, again, the Q, or the heat of the water. But what's going to be different here is that you're going to have a different mass, because the mass of the water is not going to be the same as the metal. You're going to have a different specific heat capacity, because again, the word specific means specific, right, or per the thing that you're looking at, okay? And then the change in temperature, all right? And again, every substance has its own specific heat capacity, okay? And again, that's how easily or difficult it is to change the temperature of that substance by 1 degree, okay? So for example, if we look at aluminum versus lead, okay? If we look at aluminum versus lead, at the end there is their specific heat capacities, okay? So aluminum has a really okay heat capacity, right? It's 0.9. But if we look at lead, that is 0.160. Okay? So what that means here is that if we give both of these systems the same mass, right, and we give them the same amount of heat, Q, right, it's going to be easier to raise the temperature of lead, which is why in this example here, giving them the same heat of the same mass, only thing is different is the type of metal, okay? Aluminum's going to have a change of 11 degrees, where lead is going to have a change of 62 degrees. Okay, so it is much easier to raise or lower the temperature of lead because of that specific heat capacity being so low. Okay, and again, it's the measure of energy needed to raise 1 gram of substance by 1 degree. Okay, and in later units here, we're going to look at the chemical process of phase change. Okay, so again, we'll come back to this here later. All right, so if we look at this first problem here, the I do problem, this is still a calorimetry setup. Okay, this is just a little bit nicer. So instead of being a coffee cup calorimeter, this is a bomb calorimeter. Okay, but the key that you should look for there is the word calorimeter or calorimetry. Okay, so it's the same thing. We're going to measure the heat difference. Okay, now with this here, you're given lots of information. Okay, so what we can do here is break it apart into the individual things that we're looking for. It says calculate the heat gained by the water for each nut. All right, so again, we burned them individually and we can measure the change in the temperature. Okay, we can measure the change in the temperature of the water. All right, and again, the water is the surroundings. The system is the individual nuts, the almonds versus the cashew. Okay, so we can measure the heat or calculate the heat. And again, Q equals MC delta T. All right, so we're just basically repeating that for both of these. Okay, so we have 2,000 grams for the almonds. Okay, and we have the specific heat capacity, and we have the change in temperature. Okay, and what we should notice here is that this is measuring, okay, the water. Okay, we're calculating the heat of the water. Okay, because the heat from the water, okay, heating that up or cooling that down comes from the system, right? Comes from the almonds and the cashews. But we can't actually measure the almonds or cashews. We have to measure the water around it. Okay, and one other thing that might not be obvious is that 1 milliliter is equal to 1 gram. Okay, at least for water. Okay, for water. All right, and we can talk more about that conversion later if you'd like, but just trust me on this one for right now. It's 1 mil equals 1 gram. Okay, so we did Q equals MC delta T in both of these. And again, you have to pay attention to small details, like the fact that almond is in 2,000 mils of water and cashews are in 1,000. Okay, we get both of the units there as kilojoules. All right, because again, heat should be in joules or some other version of a joule. All right, then for the last part, calculate the energy for each nut. okay? And that is the equation, all right, Q over M, all right? The heat given off divided by the mass of the individual nuts, okay? So for the almonds, it gave off 150 kilojoules, and we had 6 grams of almonds, okay? So we get about 25 kilojoules per gram versus cashews, which is 24 kilojoules per gram, okay? So almonds provide more energy per gram, all right? Because obviously it's a bigger number. All right, please make sure you're doing the we do problem, and then we'll go jump on down to the you do's. Okay, so it says a 25 gram sample of water was cooled from 23.9 to 12.7. So again, T final, that was your initial. How much heat was released? Assume that the specific heat capacity of water is that what is given to you. All right, so Q equals MC delta T. We're looking for heat. Heat is Q. All right, we got 25 grams, our specific heat capacity, and our change in temperature, which again is always final minus initial. All right, so our heat is 1170 joules. Okay, again, you got to pay attention to your sig figs. 3 sig figs, 3 sig figs, 3 sig figs. All right. Number 2, 75 grams of an unknown metal was heated to 95 degrees Celsius, placed in 150 grams of water at this temperature, thermal equilibrium. Okay, so right off the bat, that seems like a wordy problem. This is where, again, I'm going to tell you, draw yourself a picture, okay? So, for example here, what I would draw is something that looks like this, and I would write metal, okay? And then I would write all the important information about the metal. 75 grams, heated to 95 degrees Celsius, okay? Then it was placed in a container of water. Okay, so H2O, 150 grams, 23.1 degrees. Awesome. Now, both of them reached a thermal equilibrium. And what that means there, again, is that at equilibrium, they both end up at the same temperature. So 27.8 degrees. So that goes to 27.8 degrees. Okay. Calculate the specific heat of the metal. Okay, so we are looking for C. We are given the specific heat of water, 4.18. Okay, so that's what's going on here. This is the most important. Okay, so again, if these word problems freak you out, just draw yourself a picture. I promise it really helps visualize what's going on. Okay, now it says calculate the specific heat of the metal. Well, we know that if we add these together, heat transfer has to be conserved, right? If something loses heat, the other one gains it. So those are going to be equal to each other, okay? Those are going to be equal to each other. So we said Q of the water is equal to Q of the metal, okay? And again, one of them needs to be negative, one of them is going to be positive, all right? For this example, it doesn't really matter because at the end of the day, the specific heat capacity, C, should be a positive value. It should not be negative, okay? So over here we have the Q of the water, so 150 grams, okay? Its specific heat capacity, C, delta T, okay? So we started at 23 and we went up to 27. All right, on the other side, 7.5, we're looking for C, that's our delta T. All right, now this here just turns into algebra, okay? It just turns into algebra, all right? Now, if you are not the best with algebra, what I would suggest is do 2 different equations, okay? Do an equation with just numbers, okay? And then if you need to, do it with units so that you can see what the final unit should be. Okay. However, in this problem here, it should be probably the same as the other one, right? So the units hopefully aren't that big of a concern for you. All right. But again, if you're really stuck, just take out the units. Just do the numbers because that's the most important thing is getting the right value. All right. Number 3, 150 grams of ice, liquid water, and water vapor all heated by 10.2 degrees Celsius, which required the greatest amount of energy. Okay, so if we look at the specific heat capacities, it actually differs. Okay, it differs between the different waters. Okay, different forms of water. All right, so the higher the heat capacity, okay, the higher the specific heat capacity, the more heat it takes, or the more energy it takes. All right, so which required the greatest amount of energy? That's going to be liquid water. Liquid water right there. Okay, 4.1. Because again, all of these are saying to raise by 1 gram, 1 degree Celsius. Okay, so all you're looking at there is the values. All right, number 4, in an insulated cup of negligible heat capacity. All right, 100 grams of water at 50 degrees is mixed with 80 grams of water at 10 degrees. Okay, so again, if you need to, you can draw yourself a picture, but this one I think is potentially a little easier because they're both waters. All right, so again, you're going to set up two Q equations that are equal to each other. And again, Q lost is equal to negative Q gained. Again, that is an always and forever. So again, when you're making your review sheets, that would be an equation to write. Okay, this would be a helpful equation. All right, Q lost is equal to minus Q that is gained, or negative Q that's gained. All right, now we're going to figure out what the final temp of the mixture is. Okay, now here's where it gets potentially a little confusing. All right, is the fact that you're going to have T final in 2 places because both of those have a change in temperature. Okay, but make them a variable like X, and then you're going to use your algebra skills to solve from there. Again, if you need help with that, please come and see me. I'd be glad to walk you through it, okay, how to solve the algebra, but I'm making the assumption that we know how to do that, okay? Again, if you're not good with the math, get rid of the units. I promise you it will help, okay? But once we set these two equal to each other, hopefully what you notice is that since it's water, they have the same heat capacity. Okay, they have the same heat capacity. They're both liquid water, all right? Which is why in this problem, you're not even given the specific heat capacity of water because they're going to cancel out and it doesn't matter, all right? So again, when you're not changing phases and you're not changing the material, the specific heat capacities don't matter because they're going to cancel out, all right? So then when you do that and you solve your algebra, you should get 32.2 degrees Celsius, okay? So that is what we end up at. All right, and again, what you should notice is it's between our cold temperature and our hot temperature. All right, and one more thing to point out is that it is not perfectly between 10 and 50, okay, because of the difference in the mass. All right, if these were both 100 grams, then yes, it would be perfectly in between the two. Right, because they're both the same amount, they're both the same specific heat capacity, absolutely. But what's the difference here is, again, the fact that we have different masses. All right. Number 5, a hot piece of copper was dropped into 155 mils of water at that temperature, and 21 kilojoules of energy is transferred to the water. Okay, so we're trying to figure out now what is the final temperature of our water. We're still going to use a Q equals MC delta T. Oh, there it is. Q equals MC delta T. Okay, but what I need you to notice here is that in the specific heat capacity of water, pay attention to the units. Right there, it says 4.18 joules. Okay, the amount of energy that we have, or the amount of heat, is 2.1 kilojoules. Okay, so in order for those units to cancel, they either both have to be in kilojoules or they both have to be in joules. And it doesn't matter to me which way that you do it. However, I'm going to recommend, I think the easiest way is to convert from kilojoules to joules rather than messing with your specific heat capacity. Okay, so you move your decimal place 3 to the right and we have 2100 joules. Okay, so Q equals mass C delta T. We're trying to figure out what T of F is, or your final temperature. And again, you're just going to make that your X variable or your T of F variable in your math equation. This here becomes algebra. Divide over there and then add that value. Okay, so our final temperature should be 26.8 degrees Celsius. Okay, and the reason I also like these problems here is because once you're done, if you plug this back into your equation and you solve the right-hand side, you should get back out your Q value. Okay, if you don't get your Q value out the same, that means you messed up the algebra somewhere. Okay, so again, you can always go back by plugging them in and check to make sure that you got the right answer. Okay, number 6, when 5 grams of ammonium chloride is added to 100 mils of water, the temperature drops by 4.2 degrees Celsius. How much would the temperature change if 10 grams were added to 1,000 mils of water? Okay, so if we look here from 5 to 10, that's 2 times the amount. Okay, and from 100 to 1,000 is 1/10 of the volume. Okay, 1/10 going from this to this. All right, so the issue is that we add here from 5 to 100. That's a really large amount. Okay, considering the small amount of water, 5 grams in 100 mils versus 10 grams in 1,000 mils. Okay, so we have a much larger volume. Even though we do double the grams, we have a much, much larger volume of water. So the change in temperature is not going to be a whole lot. Because again, Q equals MC delta T. All right. And yes, we could set up 2 of these. Q of the ammonium chloride is equal to Q of the water. All right. But again, the ammonium chloride goes up by 2, and so does the water. It goes up by a factor of 10. All right, but when we're trying to measure the change in temperature, okay, for both of these, right there, it's going to be much, much smaller. Okay, it's going to be much, much smaller, right, because of the large amount of water. All right, number 7, 2.71 grams of fuel was burning this amount of energy. Again, kilojoules. Hopefully should ring something in your head that, okay, I've got to convert. All right, I've got to convert out of kilojoules because my specific heat capacities are always going to be in joules. All right, if the water changed from this to that, how much water was heated? So now we're just using the same equation, Q equals MC delta T. But now we're trying to solve for our mass there. Heat, specific heat capacity of water, and our change in temperature. Okay? And yes, this is going to be the most common C value we use. All right? So it might be something worth getting familiar with. All right, and then finally the last one here. Okay, 125 gram sample of metal X was heated to 400 degrees, placed in 1 kilogram block of ice at 0 degrees. Some ice melted, but after the metal reached thermal equilibrium, the temperature of the metal, ice, and liquid all remained at 0 degrees. If the specific heat capacity was this, calculate the heat lost by the metal. Okay, so that's really just a big, long thing to say Q equals MC delta T, and we're going to focus on the metal. Okay, because we weren't really given any other information about the ice or the water except for the 1 kilogram. Okay, Q equals MC delta T, mass of the metals in grams. Okay, the specific heat capacity is given to us in joules per gram, and then we can measure the change in temperature. Okay, and we solve that right there. That gives us our final value. All right, so that's the unit here. Again, it's pretty much the same 2 versions of this. It's either a straight Q equals MC delta T, or it's going to be Q lost is equal to Q gained, and we put both of our systems equal to each other. All right, so if you have any questions, let me know. Otherwise, thanks, guys.